Well, welcome back to Science in My Kitchen, the worst cooking show on YouTube. Um, so, today we're moving on. We're skipping a few more chapters because we're a little bit of time left and just wanted to go to the interesting stuff. So, we're kind of moving on to space. But first, before we actually get into space, we need to talk about how we observe things in space. So, in order to observe things, light has to bounce off of them. And have you ever thought about what actually is light? I mean, what is light? That's a question that plagued scientists for a long time. Their best answer still is, we kind of think it's this, but it's not really this. It's kind of this also, and it gets weird. But light is in a family of things called electromagnetic radiation, because it has properties of electricity and magnetism, and it radiates, it emits out. So people see this word radiation and they think bad. There are parts of this electromagnetic spectrum that are dangerous. Most of them aren't. Electromagnetic radiation includes things like radio waves, which who listens to the radio anymore, but radio waves, microwaves, you can't see it, but my microwaves right there. Infrared light, visible light, the stuff that you can see, ultraviolet light, you've probably all heard of that too, UV rays, this is stuff where it starts getting dangerous. X-rays, a couple X-rays, not bad, but a lot of X-rays can be bad. And then you get into gamma rays. Those are the dangerous things. They're the things that turn Bruce Banner into the Hulk. No, that won't really happen, so don't go outside and expose yourself to gamma rays and hope you'll get superpowers. The difference between those types of waves are the wavelengths. Wavelength is how far it is, so you got a wave. Wavelength is the distance from the top of this wave to the top of that wave. So that's one wavelength. And the closer these get together, so this has got a shorter wavelength, and then you can get really close together, or you can get really close together. So that's just a difference between the types of waves. The different wavelengths, you get different types of electromagnetic radiation. And as the wavelengths get shorter, the waves get more dangerous. So at the longest end, you have radio waves. Radio waves have the longest wavelength. Some of their wavelengths are many miles long. And they're harmless. They won't really do any damage for the most part. I mean, they're finding out you can do some things with them. So like ultrasound and things like that, you can actually break up things with ultrasound because they do have mechanical energy. And then as you get bigger, as radio waves get larger, they turn into microwaves. As the wavelengths get even shorter, you start getting infrared. And then you get this really thin sliver of just the right wavelengths of light that is visible light. And then just past that, you get into the ultraviolet light, UV lights, and then X-rays, and then gamma rays. Like I said, the farther that way, the shorter wavelengths, the more and more penetrating power they have. And then once you get into the UV and X-ray and gamma, they also are what's known as ionizing radiation, and ionizing radiation is the dangerous stuff. Your microwaves, I'm pointing at a thing you can't see. Wait. Microwave. Microwaves are not ionizing radiation, so yes, it's radiation. Ooh, spooky word. But it's not dangerous. But don't sit in your microwave. I mean, it will cook you, but it's not. The microwaves themselves aren't radioactive or anything like that. They're actually safer than visible light. Now, all electromagnetic radiation travels at the same speed. We know that speed as the speed of light. I'm going to say it in a way that you don't know. The official speed of light is 300,000 kilometers per second. It's fast. It's really fast. In units, you do understand, sort of. It's 186,000 miles per second. Now we do miles per hour. So to convert this to miles per hour, multiply it by 3,600. So if you take this number and multiply it times 3,600, you'll get it in miles per hour. It's fast. It's really fast. Give an example of this. This is roughly 7 times around the Earth in 1 second. So fast. Now that comes with some weird things. You'll see dates for things in the universe. One of the ways they've determined those dates is figure out how long it takes for light to get here from there, and then do some math. That's where the word light year comes from. Light year is the distance that light will travel in 1 year. And things in space are really far away. The sun is a little over 8 light minutes away, which means it takes a little bit over 8 minutes for light to get here from the sun. So if someone turned the sun off right now, we wouldn't know it for 8 minutes, a little over 8 minutes. All right, now, the way we observe things in space, we use telescopes. Now, telescopes are just a way to magnify the incoming light, so we can make things bigger. There are 2 types. There are refracting and reflecting telescopes. Refracting telescopes, they magnify the light by bending it. They have convex lenses, so they've got a lens at the front of the telescope. So you're back here, you're back here, looking at, well, you're back here. The light comes in and it bends this way, and it bends that way, and then it passes right here. It actually expands and magnifies the light there. If you own a telescope, you probably own a refracting telescope. They're the simplest kind. They're light, but they're kind of limited by length of this thing. All right, reflecting. So these use lenses. Reflecting telescopes reflect the light, so they use mirrors, and they use concave mirrors. They work a little bit more differently. So the light comes in, so there's a mirror back here. The light comes in here and reflects off of this, comes in here, reflects off of this, and then there's another mirror right here that reflects the light up to here, and it has the same property in that it magnifies the light. These can reflect more, but you have to start making them gigantic, and the mirror starts getting too big, and the mirror actually starts getting so big that gravity affects it and warps it. There's actually a limit to how big either one of these can be in space. If you've seen the big observatories, things at the top of a mountain where the roof opens up and the thing sticks out, those are giant reflecting telescopes. I believe there's one at Emory. There's some other problems with these. Telescopes have to look through our atmosphere. We don't think about it, but our atmosphere is actually kind of thick, and it affects the way light travels through it. If you've ever gone out at night and noticed the stars are twinkling, they don't really twinkle. You're just seeing the light refracting through the atmosphere. And then also, if you live near bright lights, you can't see as many stars. If you've ever been out in the middle of nowhere, you may have noticed that you can see more stars. So to combat this, they decided, let's put a telescope outside of our atmosphere. So they built the Hubble Space Telescope, which is just a satellite with telescopes on it pointed away from the Earth. And they've allowed us to see really deep into our universe. It was launched in 1990. They realized that the pictures they were getting back weren't particularly good. And that's because they figured out that they made some miscalculations when they were manufacturing the mirrors in it. So they had to go repair it in 1993. They basically put contact lenses on the Hubble Space Telescope to correct some vision problems it was having. They've had to do a couple more minor repairs since then. But any of the images that you see from space lately have either been taken from the Hubble Space Telescope, or they also use other types of electromagnetic radiation. There are radio telescopes. Radio telescopes, instead of picking up light waves, pick up radio waves, because all things that give off light also give off radio waves. And they can put those together and make images. If you remember the pictures of the black hole that were published earlier this year, those were taken with a radio telescope, not a visible light telescope. Advantages of that: radio waves are not affected by the atmosphere, so you don't have to worry about refraction. They're not affected by weather. They pass right through clouds, and they can use in 24 hours because daylight doesn't really affect them either. All right, that's it for today.